Then remind it over and over again, and now you actually know that in a way. But if I am looking at any property of a canonical ensemble, or any property in statistical mechanics, I'm saying that that property, in this case the internal energy, is defined as the average of the energy the system has in all states, weighed by the probability of those states. So this average sign here means it's the weighted average, where each state has a weighing factor in it, depending on how likely that that state is occupied or is not occupied. And that weighing factor is, of course, the probability of the state. And the probability then itself is e to the power of minus the energy of that state over kt divided by the canonical partition function z. Now, from that one, we then got all these kind of functions. But what we haven't really talked about yet is what happens if we have not only one system, but we have many systems. We talked already kind of implicitly about that. We talked already that we have like a gas or so. And gases usually consist of more than one atom. Now, what would be the canonical partition function of our system Z if we don't have just one atom or one molecule in the gas, but we have n molecules in the gas? Now, the result out of that one is quite straightforward. The probability that molecule I is in state J and molecule L is in state whatever, other index C1, that is just a product of those probabilities, correct? If the gas molecules are independent from each other, which by and large they are, they don't react so much, then the probability for any one combined state out of two gas molecules is the probability for the one molecule to be in one composite state times the probability of the other molecule to be in the other composite state. And it turns out the same is true for Z. So if I want to have the canonical partition function Z of a system with n particles, and each of those molecules in the ensemble has a molecular partition function small z, capital Z left, small z on the right, then this capital Z is given by the power of the molecular partition function to the number of particles we have. That is just the probability of having n particles, and each in state x or y or z and so on, is the probability of these n kind of individual probabilities. You also probably notice that the z over here was the sum over there over I e to the power of minus ei over kt. And then if I had z squared, that would only sum over I e to the power of minus ei over kt times the sum over j e to the power of ej over kt. And if I were to multiply these things out, then I would have here, as let's say it starts from 0 over here, then I have e to the power of minus e 0 over kt, the first one in this sum, and then is multiplied with the first one in this sum times e to the power of minus e0 over kt, and then there will be many other kind of things out of multiplying those two sums together. But this one over here gives me something e to the power of minus e0 plus e0 over kt, and then many other terms after that. So what I'm really doing is, if I'm multiplying the z's with each other, I'm adding up the energies in here, and I'm just getting way more terms in combination. So maybe that also makes it clear why the normalization for the probability would really see is has to be going with the power of z to the number of particles. Now, if I have this one over here, what implications does this have for all the formulas which I have on the right? And the astonishing thing is not much. What's the internal energy of a system? Kt squared d ln z by dt. But now we're looking at the system out of many particles, and we're not taking z here, but we're taking capital Z there. Now, if I plug this one in here, it is kt squared d ln z to the power of n by dt, correct? So then ln of x to the power of a is a times ln x. So it is kt squared d of n times ln z by dt. N doesn't depend on t, so I can put it in front. So it is n times k times t squared d ln z by dt. N, the number of particles which we have, times k, is the same thing as the number of moles of the particles I have, times r. T squared d ln z by dt. Okay? So the only thing which we find for the internal energy, if we use a canonical partition function, which is just a certain power of the molecular partition function of the system, is that we just get a factor of how many particles did we have in front of them. The particles don't interact. The internal energy of the system of 10 or 10 to the 20s particles is just 10 times or 10 to the 20s that of 1 particles. We have non-interacting particles. Does it all make sense to everybody? There's one thing which I kind of glossed over. Molecules are usually indistinguishable. And if I have the probability of n indistinguishable objects to be in a particular order, then I need to divide by n factorial still here. Because it doesn't matter whether molecule A or molecule B is in state A or in state B, because it could also be the other way around, because we can't distinguish them in the first place anyway. Now, if I start out in this way, then I'll have one more thing over here, then I'll have over here still divided by n factorial, correct? And that is what I'm taking the logarithm. But now, you know that the logarithm of a times b is a logarithm of a plus a logarithm of b. Which means that when I'm over here, then the only distinction I have over here then is that I'm doing, this is in the denominator, so it's a minus sign, minus the, minus the logarithm of n factorial. And that is what this whole thing is about, right? If I have it here in the denominator, then I can pull it out of its own logarithm. But if I take the first derivative, and I can take first derivative here on the left, and then I have here on the right also a first derivative. I don't have the n, so it's just a kt squared d of the logarithm of n factorial by dt. But n factorial doesn't depend on t. So the whole first derivative of this one here is just 0 minus 0. No change whatsoever The only place where we have a difference is here for the entropy. For the entropy, it's not the first derivative, and so for the entropy, we would have the factor n factorial survive. That's it over here. So it becomes here then minus k times ln n factorial. Okay, that's the reality. The 0 point of the entropy is shifted that way. The 0 point of the entropy is shifted. Where the 0 point of the entropy is, nobody can define anyway. But the entropy 0 is shifted if I have one particle or many particles. And it's shifted by k times ln n factorial. Okay, if I have my minus k times alpha n factorial over here, how do you type that in your calculator? Because if you have 10 factorial, you can type it in your calculator. But typically we have a roll of particles, and then you have 10 to the 23rd. Don't try typing 10 to the 23rd something factorial in your calculator. It will not work. Because 10 to the 23rd times 10 to the 23rd minus 1 is already something on the order of 10 to the 46, and so on. So it will explode way beyond what your calculator can do. How do you type it in your calculator? Now, for typing something like ln of n factorial in your calculator, there is a way of approximating it. Because ln and n, the ln and the factorial, they kind of work against each other. This keeps making it bigger, 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 and this logarithm then makes it much, much smaller again. And so you can approximate, if you ever need, that ln of n factorial is almost the same thing as n times ln n minus n. So if you ever need to calculate for a mole of gas particles in entropy, where you have this extra term over here of k times ln n factorial, then your k times ln n factorial becomes k times this thing over here, n times ln n minus n. And that is something you can put in your calculator because there's no factorial here. If you have ln of 10 to the 23rd, that will be just like 100 or so, and then 100 times 10 to the 23rd minus 10 to the 23rd is just 99 times 10 to the 23rd. Something else. So very easy to be done in a calculator. This whole thing here has a name, and it's called Stirling formula. But it's just math. So it's not anything particular to statistical mechanics, but it's often very useful. Okay. At this point, I believe I'm done with what I wanted to teach you on statistical mechanics. Do you have any questions? Yeah. So then also at this moment it stops that stuff as on the midterm. So only up to here things are on the midterm. Beyond here it's not anymore in the midterm, but it will of course be defined. Okay. And let me get that screen down. The next thing I wanted to talk with you about is, now we learned a ton of things about how gas particles react. We learned, before we started, with statistical mechanics. That molecules are so and so big, and they need to have about 15 distances. In a gas, like in this room, they have about 15 times their own size distance to the nearest gas particle in every which direction. And they zip through that very, very fast, on the order of a picosecond. So about every picosecond they run from their own location to the location of the nearest particle. And then about every nanosecond or so, they hit the neighboring particle. We had that all on the slides a couple of weeks ago, when we transitioned from gas theory into physics. So now we want to talk about kinetics. Really, we want to start with kinetics next Friday after the midterm. But we want to lay the foundation for that. And if those molecules now zip around, what they will do is they might hit some other particles, and if they hit other particles, there is an interaction potential between them. Somehow the energy, the potential, varies with the separation of particles. And let us now assume for a moment that our gas is atomic, meaning consisting of atoms and not diatomic molecules. Then one of the gas particles might be the red circle over there, and the other gas particle might be the other red circle. And most of the time they just fly somewhere here, but sometime they might come closer to each other. What will happen? Now what happens is that the energy of the system will change. The energy of the system will change because the electrons of the neighboring atoms feel, oh, there are other electrons available. There's also another nucleus available. I could be bonded to both nuclei. Would be really nice if the other electron wasn't there, because then I would have both nuclei just for myself. But at least I can still interact with the two nuclei at the same time. I find a better way of arranging myself. And as a consequence, the energy goes down. And really, energy is the only thing, as we learn, which atoms or molecules know. So as I'm coming closer and closer with a red atom, while the other red atom is at here, so one atom is here, and the other atom is coming closer and closer. If they are far away, nothing happens, they don't know about each other. But if they come closer and closer to each other, then the energy is going down, it's going down, it's going down, it's going down, until there is the minimum energy position. That is what people call the bond length. That is the optimal position for the separation of the atoms. And if the atom had enough momentum coming from over here to run into this one, then it might actually collide into this atom and come closer than the optimal distance, because it had all the momentum, it had all the high speed which we calculated now. And then, if they were to come closer, the electrons start to repel each other, and as a consequence, the energy goes up again. And it goes up dramatically, way higher than no interaction. Up there is no interaction. The 0 point, if you wish, of the whole thing is here. And if they come close to each other, it goes way up in energy. They will not get much closer than that. They don't have enough kinetic energy. Kinetic energy needs to pay for any closer approach than coming here. So, the atoms can bond. Or not. They can just bounce off each other and run away from it. How can we try to understand it? One way to try to understand the interaction between those atoms is to say there is an interaction potential. And quantum mechanics can describe that very precisely, depending on how small the atoms are, or very imprecisely, depending on how big the atoms are. But quantum mechanics can describe it. But there's lots of effort involved in using quantum mechanics for that, even with today's computers. Over my lifetime, it has been gone from nearly impossible, even for simple atoms, to readily feasible even for complicated or somewhat complicated molecules. And over your lifetime it might go to even better understanding. But no matter how good the understanding is, it's usually used after this increase in computer power by us people trying to look at even more complex situations, involving even more complex atoms, involving even more complex molecules. And so very frequently we still need to have an easy way of looking at that. And that is, we assume a mathematical formula which gives the shape of this potential, this blue potential over here. Rather than solving quantum mechanics precisely, we make some assumptions about it. And the typical assumption people use is the Morse potential, which is shown over here, the blue. It is not as simple as a harmonic oscillator. It is not just a square parabola over here. It is wide on this side, it is narrow on the other side, it is asymmetric, and the Morse potential over here makes a fairly good effort in describing what is the interatomic interaction. It is not exact, it doesn't try to be exact, it's not quantum mechanics, but it's something useful to, especially if you want to model hundreds or thousands of atoms, then it's a quite good approximation. Now, quantum mechanics will also tell us something about vibrational states, and the vibrational states tell us something about the curvature over here, and then I can always adjust the Morse potential by adjusting the dE, the A, and the RE here by getting the right separation, getting the minimum of the Morse potential over here, getting the right bond energy, the right depth of the potential over here, and also the right narrowness of the curvature over here, whether the curvature would be like this or the curvature would be like that. Those three things I can adjust in the Morse potential based on reality. Bond lengths, I might know the bond lengths from X-ray crystallography, then I adjust the RE. I might know the binding energy from some calorimetry, electrochemistry, whatever, then I can adjust the dE accordingly, and this curvature down here, I might know from where are the vibrational levels, and then I can adjust the A, and I get a very nice description. So this is how computational chemistry works if people work in what they call molecular mechanics. Because really it's just mechanics. We say there is an interaction between them, it's an interaction potential, it is not really involving quantum mechanics. I can just do the normal mechanics on this kind of potential. And that is widely used in the biological arena. If you want to understand the interaction between biologically relevant molecules, they are usually really big, and they are way too big that quantum mechanics can give you many information. You can't really model on a quantum mechanical scale the whole molecules and their motion with regards to each other. It just doesn't work. It's too complex a system. And so people simplify it by a mechanical approach, which involves interaction potentials like the Morse potential. If you are interested in doing that, such calculations, Chia and Chang is the faculty here at UCR in the chemistry department who's doing that kind of modeling. Then there is another potential, not the Morse potential, works however very similar. It's called the Leonard-Jones potential, and often it's also referred as a 6-12 or 12-6 potential, because the repulsive interaction over here is with the 12th power, and here the attractive interaction is modeled as a 6th power. And the sigma over here, the epsilon, are adjusted, that you have like a binding energy and something like the right bond length. Which one to use? Morse potential has 3 parameters, so you can adjust 3 things. Lennard-Jones potential has two parameters, you can only adjust two things. Moreover, the way computers works, it is sometimes much easier to have a 12th power calculated than an exponential. Because for an exponential, you probably want to calculate it by a series expansion of an exponential, and that has many elements in it. So from computer perspective, this is much faster than the Morse potential, but it also offers you one parameter less. If I think about the reaction between two molecules, I can start modeling it. If I have a molecule like this one here, red-blue, then maybe here at 5.5 or so is a location where my blue atom is. Then it's here at 4.5, what distance then maybe is 1 angstrom between them, is where the red atom is. And at 0, there might be my green atom. And if this molecule happens to have some kinetic energy moving in this direction, and if I know there's also a Morse potential-like interaction between the green atom and the red atom, with the energy over here, then I can put, if I'm interested in what the red atom is going to do, I can put those two Morse potentials just to each other. And I'll get that, right? I just added those two lines. I just added the Morse potential on the left of the red interacting with the green, and the Morse potential on the right, the red interacting with the blue. I just put them together. I know what my red atom is doing now, and it looks like this. There's one minimum over here that corresponds to, I have the bond between red and green, and then there's another minimum here that was the bond between red and blue. And in between, there's barium. So, that is part of the activation energy then for the reaction. Because that looks very, very similar to what you've seen all along for barriers for reaction. I have an initial state, a transition state, and a final state. It's exothermic this way around, it's endothermic this way around. So if you're thinking about plots with a barrier and an activation energy, an initial and a final state, they are really just superpositions of interaction potentials. They are really just like this, cut off at this point. Cut off at that point, I get here. So you've seen them already in grade school, not realizing they are really just cut off plots of interaction potentials. What is on the x-axis over here? If I had the very simple setup here, where I have the blue atom there and the green atom here, and the red one moves between them, then it's of course the position of the red atom, which is on the x-axis. The reaction coordinate for that reaction is the position of the red atom. But the reaction coordinate can be much more complicated. Maybe the molecules are tumbling in space, and only at some particular relative orientation they can undergo the reaction. What I then do is I look, what is the lowest energy pathway? Where can I get to the smallest variant? Where is this transition state the lowest? And then I might make a pathway, look at the pathway where this barrier is the lowest. And along that, I say, that is my reaction coordinate. I simplify everything to one coordinate, even if that one coordinate is not one straight line in space, that can involve very complex motion of the atoms. Okay, what we did right now, what we did is we have an H2 molecule, red and green and red before, and I have another H atom, and this other H atom is coming at speed towards this hydrogen molecule. Then at some point I can get to the transition state where they are all close to each other, and depending on what happens, either C will bounce off from AB and run away this way, or C will snatch B away and A will run in that direction. that is really the only two options that they are. Either it reacts or it doesn't react. So, if I'm looking at my reaction potentials, then I'm coming to what people call an elbow plot. Obvious reason why it's an elbow plot. This way, but elbow plot. So what you see in such elbow plots is if we have a large separation between A and B, if this is far away from each other, then the only interaction is really the one between B and C. The one between B and C. And then if it's close, then I'm very high up in energy, and then I'm going lower in energy at the optimal separation at the bond length between B and C that's here, down in this kind of muscle of the elbow. And then if the B and C separation gets even farther, the bond between B and C is stretched, B and C are far away from each other, then it goes up in energy again until I get over there. And the same thing holds true up here. If the separation between B and C is really large, if this separation here is really large, I'm really only interested in the interaction between A and B. They're the only ones which are close to each other. And if A and B, AB axis here, if they're really close to each other, they repel each other, it's very high up in energy, and then it goes down into the valley, where in the bottom here I have the optimal bond separation between A and B, and then over here it goes back up in energy. So you can have a 3D plot of that if you wish as well. It would be a 3D plot like this one here, where there's a low energy pathway out there. So it's a low energy pathway, this one over here. The reaction coordinate is a dashed line over here. The shortest pathway which connects the initial and the final state to each other, which goes over the minimum energy configuration. And people calculate those elements. So that is then more than just Morse potential, which people use. It is then more quantum mechanical like, but for far separation, they look again very much like Morse potentials. And if you have such a potential energy surface over here, then you can really imagine you're just playing marbles on that. The system, the whole system, is then represented by one marble. And you are throwing your marble into this trough over here, like this, and you can see, depending on how you throw it, it might run up here and bounce back, or it might get this corner over here and fall out over here. Depending on how you throw the marble in that system, depending on what momentum your particles have in the beginning, you'll find you either get to the product or you stay on the reactant state for the system. And you can test that out in a computer by having the mechanics of how the marble is rolling in this potential tested out with many, many different starting configurations, and in which starting configuration, in which momentum of the system would I be able to get through it, and in which momentum of the system in the beginning I would not be able to get through it. And then that gives you naturally the probability for the reaction to happen. It gives you the probability of when you came as a system AB, where C was bouncing into it, whether it stays AB and C just bounces off, or it becomes A with a new molecule, BC. You call this approach of trying to roll the marble through that potential in a computer, trying it over and over again, a Monte Carlo approach. Monte Carlo is a casino place in Europe, just like Las Vegas could be. So you are just trying it out many times in the hope that sometimes you'll be successful getting through there. That's what one of the expressed is. Okay, does it make sense? So that is what people call Monte Carlo. But whatever we call it, somewhere in the middle of this one is the barrier. Somewhere is the barrier, and somewhere is the transition state. the transition state we need to overcome. Whether it is the product states are higher in energy than the initial state, the reactant state, or whether they are lower depends. And that depends whether we have an endothermic or an exothermic reaction. But for how fast and how likely the reaction will take place, that is not relevant at all. What is relevant for how fast will the reaction take place is how high is this barrier? Which fraction of this throwing the marble into that potential will lead to the success that we have a change in the bonding, and which fraction of throwing the marble into this potential energy, well, surface will just make the marble come back out to the first place and not the normal reaction. So, if the subject matter for the next 2 weeks is now kinetics, the study of how fast are reactions, then we really need to learn something, how we approximate how the molecule is running in that trough over there, and how likely is it that it will be able to come out on the other side in the product state, and how likely is it that it come out in the first place. But also, how often does a system really try to do it? How often is a marble being thrown into reality? Because how often the molecules tries to undergo the reaction times the probability for each attempt to be successful, that will give us the rate at which the molecule will react. So it is again something which has to do with energy, how big is the barrier, that will determine how likely it is that the molecule gets to that high energy state. And then times how often does a molecule try. So, and all of these things will define the rate constant K. It will not define those concentrations or so. Dealing with the concentrations is what we did in Chem 1. Here we want to deal with the Ks. We want to determine what is that K. And we will come to the conclusion that the K is very similar to our canonical partition function. That the K is e to the power of minus the activation barrier for this reaction over Kt. So that is giving us something which indicates how probable is it that the molecule has sufficient energy to overcome the reaction barrier, and the whole thing needs to be normalized, but people don't write it as 1 over z, rather they put an A in front of it. Now, A could be 1 over z in some z for this reaction. Doesn't make it, but they call it A in front of it. And the A also includes how often does a molecule try. So, in that regard, like we calculated, the molecule average is here, it needs to go 15 times its own size to come over here, where the other molecule is, and it does it every picosecond, but it hits the other molecule only once a nanosecond, and in the other 1,000 cases it misses the other molecule when it zips through its space. So the Ka over here involves this nanosecond or picosecond or whatever it is, and it involves some sort of normalization for this term. Those two are put together and are called A. The whole law, the whole formula over here is called the Arrhenius rate law. Yes, Arrhenius is spelled with that, double R and an H. And the constant A could be an Arrhenius constant. It could be an attempt frequency, how often does a molecule attempt to do that reaction. Or it could just be a pre-exponential factor because it's standing before the exponential. So those are the three names for the A. There's not only one. people talk about pre-exponential factor, about the temperature, or about the Arrhenius constant. And this one here, the delta E, that was the activation energy, this EA over here. Okay, so now we learned already how we can calculate the K, at least on principle, if we have the A and if we have the delta E. Now we're going to study that more on Friday of next week after the midterm. But let me tell you before that, figuring out what is the A, what is the delta E full reaction is an ongoing research objective in many cases. So if you're thinking about gas molecules, Jim Zhang's group, for instance, is working a lot on that, figuring out in the air, if I have air pollution, and the air pollution molecules will interact with other molecules. What is the rate of those reactions? And if you're interested in undergraduate research, I'm sure he's taking students these days. In my lab, we've been looking a lot of the rate of reactions on surfaces and seeing how molecules slip around surfaces and undergo reactions that way. In Francisco Zaera's group, they are looking at molecules impinging on surfaces and then using the Arrhenius equation to look at reactions. All over chemistry, we do use the Arrhenius rate law in order to learn something about this. And there are plenty of opportunities for you to get involved. Thanks so much. Good luck. Remember, 3 sheets of paper, front and back, handwritten by you, handwritten by you, you can grade. Otherwise, for this grade as well, same rule as well. Okay.